Okay, everyone, welcome to class number 20, Faraday's Law. And today we're going to be covering a very interesting phenomenon related to EMF, which we talked about last time, but it will generalize into some interesting properties of circuits as well as of the energy in the magnetic field. And this covers section 7.2 of the textbook. So Michael Faraday was a brilliant experimenter in the early 19th century. He inspired Maxwell with his experiments, and the Maxwell equations were an effort to bring to a mathematical, synthesize mathematically the insights that Faraday had through his experiments, and he's considered one of the great experimentalists. So we're just going to look, he did experiments in many different areas. We're going to look at his experiments involving circuits and magnetic fields and see how it leads to a generalized law for the electric field. So let's look at these experiments. Here, experiment A here is the experiment which we analyzed last time, last class, in terms of motional EMF, where we had a circuit that moved to the right, and this vertical wire here, the charges in it experienced an upward force, and that upward force served as an electromotive force to drive current around the wire. What Faraday realized, or what he realized or came upon through experiment, was that one could keep the current loop fixed in space and move the region of magnetic field, say by moving a permanent magnet in the opposite direction, so to the left, whereas here the current loop was being moved to the right. And if you move the magnet at the same speed as you had moved the current loop, you would get the same current induced in the loop. And in this case, it's harder to interpret this in terms of forces on charges, because the charges here are not moving in the magnetic field. So, and charges with zero velocity, if we look at the Lorentz force law, F equal QV cross B, shouldn't necessarily experience a force, at least to that level of understanding. So this is harder to understand in terms of the physics we've done so far, but nevertheless you see the current. And then another experiment Faraday did, was to keep both the current and the magnetic field regions constant, and to change the magnetic field. He did that using an electromagnet, a coil of wire around a hollow core, which was known to create a fairly constant region of magnetic field. And he found that if he changed the magnetic field without any motion, he would still see the current. Okay, so so these are three different effects, and he identified. He was not a mathematician, but he had a great intuition for physics, and so he came up with this idea of field lines, or a unity of field lines, and coined the term flux, and said that a changing magnetic flux through a region of space induces an electric field circulation, which then gives a current. So in all three of these cases, a changing magnetic flux, so here magnetic field stays constant and the area changes, and so constant magnetic field times the changing area gives a changing magnetic flux. We get an electric field circulation, and therefore drives a current around the circuit. Here again, we change the magnetic field stays constant. We change the area through which the current is flowing, through which the circuit flows, and we get again a changing magnetic flux. And finally, we have here in this case, we have a constant area, and we change the size of the magnetic field finally, but we still get a changing magnetic flux. So we can say that our EMF, as we've defined before, is our integral of the electric field, or the electromotive force, which in this case the electric field, dl, is equal to minus the magnetic flux with respect to time. Why minus? Well, that has to do with direction and something called Lenz's Law. So in this case, right here, if we pulled this to the right, and the current induced was in the opposite direction, it would actually, if you work it out, if the current is going counterclockwise, then the current is going counterclockwise, then it's actually going to reinforce the magnetic field which is already present and reinforce that change. And so the current is just going to increase, which then reinforces the change more, and so on. And so that violates the conservation of energy. We get a runaway current. So this minus sign is a reminder that of what's called Lenz's Law, which tells us that the magnetic field which tells us that the current that is induced must produce a magnetic field to oppose the change in flux which we see. So this is Lenz's Law. Hopefully that will be familiar from Physics 202, but you might want to Google Lenz's Law if it doesn't ring a bell. So anyway, the EMF can be written as the rate of change of the magnetic flux with respect to time, with this minus sign to remind us of the direction of the EMF. And then the line integral of the electric field, which is here, is then we can take this, we know that phi is integral of b dot dA, but the area doesn't depend on time, and so we can bring the time derivative inside and have the integral of E dot dl is minus the integral of dB dt dot dA. Okay, but now we can use Stokes theorem. We have the line integral of something is equal to minus the surface integral of something else, We know that the line integral of E is equal to the surface integral of the curl of E, but we also know now physically that it's equal to the surface integral of minus dB dt. So that implies that the curl of E must be equal to minus dB dt. Okay, the curl of E is equal to minus dB dt. Now you might say, hold on a second. We've been saying that the curl of E has been 0, and that was even a test question. The curl of E is equal to 0. But that was in the case where we had electrostatic and magnetostatic fields. So this, in other words, where electric charges were constant and currents were constant, and so electric fields and magnetic fields were constant. So if magnetic fields are constant, this reduces to the curl of E equals 0, as we had before. So it's consistent with what we had before, but now we're in a case where we don't have a magnetostatic case. We have a changing magnetic field and a changing current. Okay. And in addition, this is actually, we've come across our third Maxwell equation. Our first two Maxwell equations are that the divergence of E is rho over epsilon naught, which is equivalent to Gauss's law, and that the divergence of B is equal to 0, which is equivalent to there being no magnetic monopoles. But this equation here actually, which Maxwell wrote in close to this form to summarize Faraday's experiments, is a third of our Maxwell's equations. And next class we'll see that how we have to alter the fourth, the curl of B, to form the full Maxwell's equations. All right. So this gives rise to some interesting properties of circuits, which are useful for electricians, for those who deal with electric circuits, called mutual and self-inductance. So what does that mean? This mutual. Let's start with mutual inductance. So we have a circuit here. We'll call it loop 1, which has a current I1 flowing in it, and that creates magnetic field lines all throughout space. And if we have, so we assume a steady current through loop 1, and the presence of a second loop some distance away. Some of those field lines from B1 will thread through loop 2. And so there'll be a magnetic flux. Okay, so there'll be a magnetic flux through loop 2. Now that doesn't mean there'll be a current through loop 2, because we only get a current when there's a changing magnetic flux. So there can be a steady magnetic flux here, as long as this current is steady, and there won't be any current flow through loop 2. So just to remind ourselves, this is the Biot-Savart law that determines the magnitude of B1 in terms of the current around this loop. And we can say that the flux through loop 2 is equal to the integral line, the surface integral, sorry, of the magnetic field due to loop 1 dotted with dA2, the area of the second loop. And as a result, since B1 is determined by is proportional to I1, and otherwise is determined by the geometry of loop 1 and how it is positioned with respect to loop 2, which gives rise to the directions r hat and the distances r squared, we can say that we can write that phi 2, the flux through loop 2, is just equal to a constant as long as these geometry holds, that we don't move them. M21, which is called the mutual inductance of loop 2 with respect to loop 1, times I1. Okay, so if we double the current through I1, we double the flux through loop 2, and this is the coefficient of proportionality. And it turns out, and this is a several line derivation in section 7.2, which is, you could certainly follow, but I don't want to bog down this video with too much mathematics. We could also consider loop 2 as having current, and those magnetic field lines as threading through loop 1, and therefore loop 2 would cause a magnetic flux through loop 1. And it turns out you can show that the mutual inductance of loop 2 with respect to currents in loop 1 can be written in this form: mu naught over 4 pi, a double line integral over dl1 and dl2. But notice this expression over the distance between L1 and L2, as these both range over both loops. but in any case, this is symmetric with respect to 1 and 2. And so we find that M21 would be the same as M12, because if we exchange 1 and 2 here, we get the same result. So this shows that the mutual inductance M21 is equal to M12. They both just depend on the geometry of how the loops relate to each other. And that's actually a little bit amazing if you think about it, that we can write phi, the flux through 2, as equal to M21 I1, and the flux through 1 is equal to M12 I2, if there was a current going through 2, and those M's turn out to be equal, no matter what the shape is or the orientations. Okay, so that's mutual inductance. Self-inductance happens because when a current flows through a wire, there's a magnetic field which threads through the loop itself. And so we assume if that current changes, if that current I changes, the magnetic field through it changes. That'll give rise to a changing magnetic flux, and thus a electric field circulation, or an EMF, which could increase. Well, and generally it'll oppose the change in current, which induced it. So we can say that the flux through the loop is proportional to the current. If we double the current, then because of the Biot-Savart law being proportional to the current, the flux through the self flux is just going to be proportional to I, and the coefficient of proportionality is called the self-inductance. And so therefore we can write the EMF induced if the current changes would be minus d phi dt, according to Faraday's law, but assuming dl dt equals 0, that is, this geometrical factor L does not change, the shape of the loop doesn't change, the only thing that's changing is I, and so therefore we have minus L di dt. So this is a formula for the EMF induced in a loop due to its own self-inductance, the fact that it creates a magnetic flux within itself, which when changed will produce an EMF to oppose the change in current. And the minus sign is again a reminder of Lenz's law, that it opposes the change in current, which produced it. Okay, so this equation here, this self-inductance, is actually quite useful to talking about energy in magnetic fields and energy in, let's say, configurations of currents and fields produced by those currents. So if we start off with the work done on the magnetic field, so if we have the work done on a circuit is going to be the current times the EMF of the circuit, because the current is the charge per time, and the EMF is the voltage, which is the energy per charge. So energy per charge times charge per time is energy per time. And so this would be the amount of work per unit time. Epsilon I would be the work per unit time done on the circuit. But done on the field would be the opposite because of conservation of energy. So the amount of work or energy put into a field, say a magnetic field whose flux is changing by the circuit, would be minus E times I. And then since we established that E for a single circuit is minus L di dt, we just have that becomes Li di dt. So that we have a minus L di dt times a minus I, and that gives us Li di dt. So this is how fast energy would be being pumped into the magnetic field. So integrating this, we find that by the, well, the best way to check an integral is just to see if we get the right derivative. So if we differentiate both sides of this, we get dw dt is equal to 1/2 L times 2I times di dt. So the 2's cancel. We get Li di dt like this. So we have the energy in the magnetic field of a circuit with inductance as 1/2 L I squared. Now the magnetic flux is the integral of B dot dA, as we know. That can be written, B can be written as the curl of A, the vector potential, dot dA. And then by Stokes theorem, the integral of curl of a vector over an area is the integral of A over the perimeter of that area. Okay, so that means we can say that phi is equal to, which we said in the last for a single circuit was equal to the inductance times the current. Okay, that was on the last slide. Let me just remind you. There it is. Phi is equal to Li. So we have Li is equal to the line integral of A dot dl. So this is a bit of a derivation here, but coming back up now, we can take we can pull out a 1/2 I here, and we're left with Li, and Li is the integral of A dot dl. So we have 1/2 I times the line integral of A dot dl is the total energy in the current, the circuit with current flowing and with the magnetic field that it has produced. So we can pull this in. The current points in the direction of dl, so we can write this as A dot I dl, and we can generalize it since I dl, I is a linear current, dl is a linear displacement. We can generalize this if we want to integral over a volume of A dot j d tau, where j is the current density, the current per area times the volume element. Okay, we actually did that before with electricity and magnetism. Okay, so this expression here is the energy involved, because it's integrated over volume of a set of a current field configuration where the field is represented by its vector potential A, and the current, which could be in a wire or could be in a flowing set of charges in space, is represented by J. Okay, so this would be the current field configuration. And then it's possible to show, it takes a few more lines, and I've already done a fair amount of derivation on this page, but in a few lines in section 7.2, you can show that this integral of A dot J can be written in terms of an integral over volume, all space, of the magnetic field B. So that means that we can interpret B squared over 2 mu naught as the magnetic field density, the energy density in the magnetic field. Because when we integrate it over all space, we get the total energy, magnetic energy. And you might recall that we had a similar expression. It was actually epsilon naught over 2 e squared for the electric field. So a very similar expression for the energy density in the electric field. So for both the electric and the magnetic field, we have these constants out in front, but basically the energy density goes as the square of the field. Okay, thank you for your attention, and we'll do some problems in class, and we can look forward in our next class to getting the full complement of Maxwell's equations. Thanks very much.